next is tensions. I think I will go through it some of the details in the lectures that we cover. Just a revision, 5 minutes maybe, to just recapture what we done. When we have when we try to pull something from the two ends, that is the tensions, right? So that's tensions that we are talking about, generally the steel members. So when you have a members and you are pulling at two ends, that is the tension behavior that we are designing it. When you don't have a hole, your materials may be yield. There are two kinds of failures, yielding and fractures. When there is no hole, you have a yielding behavior, yielding failures. Yielding meaning you will permanently deform your materials. You have seen that yielding in the experiment, that when you see the deformations with your visible eye saying, there is a permanent deformations, right? That is a yielding. Another one, when, well, the steel members or tension members generally have a connection, so you need to put holes to have a bolting and all. So when you have a hole, at that particular point where area is reduced, you can look at the area here, it's area reduced, you will have fracture. So there is another phenomena that will come, that is the yielding and fractures. If you want to say the yielding, stress is equal to load over area, yielding is FSY, you know these diagrams, that this is the point that is your yielding point, right? If you reach, if your materials, if you load your, if it is zero load, it will be here. But if you keep increasing the load, it will reach at one point and it will reach the yield point. So that is the yield strength. So we have stress, yield strength. Standard saying that your load is NT. So just a symbol, gross area. The area is like when you take the cross section area, this cross section area, right? Not this area, not this area or not this area. How do you know? When you apply the load, the perpendicular area to that cross section area to that load. If you are pulling this way, of course you take this area. That's the gross area that we talk about. When you pull the perpendicular area, that cross section area that you take gross area. So there is no rules that you need to take this one. If I pull this way, I need to take this area. I hope it makes sense. Now, so that is the yielding, and I can show it to you in the standards. They have an equations. That's yielding failures. There are two kinds of failures. One is yielding, another one is fractures. Yielding one, everyone understand, when there is no holes in that area, you will get the yielding failures, right? And by the way, we are working on the section 7 now. Section 7 is chapter 7, standard saying section 7, and section 7 that we're going to refer this week. Right, so these first equations, everyone understand, NT, and basically that's the theory behind it, that I prove it, you can see, right? And that's NT equal to AG times FY. AG stand for the gross area, the total area that experiencing, and FY yield strength, generally speaking, FY we take it 300 megapascals, 320 megapascals, we will say it, but if you take it 300 still it works. So that is the yield strength, 300 straight away, all the one steel that we have about 320 megapascals yield strength. So everyone clear on that one? Next one is a fracture. Fracture has an equation. Again, you don't need to remember that fractures 0.85 KT net area and FU. Okay, these are the parameters for the fractures. And those fractures parameters that I'm going to take you through is when you have a hole. When you have a holes, you can look at this behavior here. The red one that you can see the diagram is without hole. You don't have any holes. You pull two ends and you will get that behavior. Very nice ductile behavior. Ductile behavior meaning you have this kind of behavior and then, this kind of behavior, and then it bang. We like it, standard like it. We want that. Sometimes not good. This is not good. Standard don't like it, heavy penalty to the capacity factors. This one we like it. Look at the red one. We know have hole nicely stretch, elongated, fully elongated, and then it will separate or it break. It give you plenty warning before it fails. So if these buildings reach its failure mode, it will should extend, and then it should fail. Right. So that's what we want to design, the red one. But we can't avoid it. We put the holes. We can't have a member that we need to connect the one member to another member, right? We can't have just standalone members in the buildings. So we need to drill the hole to connect with each other. So when you drill the hole, the blue one going to follow. Look at that. That is less ductile. That it will just come back here and it will fail. So that is not significant hole. Let's say you have one hole that you can see down below blue one. Someone say that, okay, I have more connection and I drill more holes. Then you have a problem. If you don't reach yield point, this is the yield point. We want to reach yield point and it does not release because you have plenty of holes and during that holes it will break. So to take into account, because your FY is 440, we will going to experience where it is, but this won't reach 440. So standard saying that you reduce 50% your FU. Because someone might say, people, how do I know whether it's significant hole and non-significant hole? Is there a rule that one hole is a non-significant, two hole is significant? No, there is no such rules. Standard saying that if you have a hole, you can just put 0.85, 15% reductions, and that is your FU reductions. Okay, so that is given here. You don't need to remember all these nitty-gritties, right? It's just for you to just say where all this coming. So 0.85 FU, and FU is that ultimate points 440, and I will show you where they are. KT. Now the KT is called correction factors, and this is written here. KT correction factors distribution across flow 7.2, and I need to explain you KT, by the way. Let me explain you. Now let's say this first figure, red one on the left side. Let's say you have a L equal angle channels, and I hold it at one end. I think I don't have that specimen. I don't have. Okay, let's say I hold it this one at one end, fully hold it, like I hold it these pens, fully hold it, and some other guy comes and they stretch it the other end. So these whole cross sections will have a uniform stresses. Right? Because whatever the point, uniform stresses, whatever the point it will stretch, the same, this will going to be extended. Right? So this is called uniform stress. When you have uniform stress, your correction factor, standards like standard said uniform stress, no eccentricity, we will give you KT equal to 1. That is a uniform stress. Now someone said that, okay, but we don't have this arrangement. Let's hold your only this base plate. And someone again pull it, this one. So this point will be less going, this point will go more, non-uniform stress. Then your KT would be less than 1. Does it make sense? So correction factors, two options, KT equal to 1 when you have uniform stress. When you have non-uniform stress, your KT is less than 1. Again, I-beam, if someone hold the surface this way and someone pulling the everything, then uniform stress KT equal to 1. Someone just holding this edge and holding this edge, these are free to go. This will try to pull more, this will try to pull less, and you have non-uniform stress KT less than 1. And how do you gonna find it? That KT you're gonna find it in these tables. Now in these tables, there are 7 cases given to you. 7. 1, 2, 3, 4, 5, 6, 7. From these 7s, I will classify, I will remove 4. I will just set 4 and 3. So let's say 4 and 3. That's how I just look at these tables. I look at this like this. And I will look at this tree. I will look at either close this one. So I will look at into 2 zones. I don't look at the whole table straight away, because you will need to say once you need to divide it into 2 parts. So what is this zone? It is called back-to-back connections. Back-to-back connection. Let's say this is a plate. This is a plate, meaning this is the plate that you're not designing it. This is the plate is there, solid plate. You are designing these 2 members. Someone pulling it, then you have uniform stress, your KT equal to 1. Another one, let's say this is C channels. You have KT equal to 1. If your flange is connected, I think this is flange. This is flange. Sorry, wave is connected, the long member connected, then you have KT equal to 1. This is a plate that we're not designing it. Let's say this is the kind of I-beam and this half I-beam, your KT equal to 1. So this is how I look at the tables. Just look at these 2. It is back-to-back connections. Back-to-back connections, KT equal to 1, uniform stresses, like twin angles, twin channels, twin T's. Okay. Then if I'm not in this category, I would be in this category. again, you have a plate and you have this angle. You either have 0.75, 0.85. This is again two angles, C channels, 0.85 and 0.90. So maximum reduction, you will get 25%. Okay. Does it make sense how to use KT? 7 cases. Just look at these tables in two different zones. Don't write anything on the standards. If you have a cheat sheets, you can just put it those details on the cheat sheet. But I think it's easy. Once I explain you, it is easy to see that you have just divided two, KT equal to 1 and KT less than 1. Non-uniform stress, uniform stress. All right. So that's KT story done. Yeah, I think that's it. And then 0.85 we discuss. Net area we will look at in the examples, the net area. All right, any questions? I think this we spent about 15 minutes on revising it before we go on this exam this way, because all right, so this is an example in your workshop. Rework the example number 1 in the lecture notes. Okay, that's I already put it here. This is the examples that we done yesterday, and we need to rework on that one. For the same orientation of the angles. So like yesterday, we have this one. This is the plate. And we want to design, we have given this equal angle that we are designing it. And it was bolted here. That configuration is given to us, and we design this. We design this one, or we calculate the capacity for this one. Now someone said that, okay, this red guys will comes down here, and you have this. You have this, and you do the bolting here instead of this one. That's the configurations. Like yesterday, we done the calculation on this one. Same thing. We want to do it for these 75, 56 equal angles. 75, 56 unequal angles. Same orientation of the angle. Legs instead are connected to the single gusset plates by M20 bolts. So this is a gusset plate, and we are connecting to the M20 bolts, and this one would be short leg, right? I hope it makes sense. And we need to, this is 75, 56 unequal angles. Right, what is the questions? We need to find the design capacity. We need to find a design capacity of this 75, 56 unequal angles. Right, I think in the lectures example 1, look at this, we done this NT and all these calculations. I think we're going to do it same things, but just in the different configurations. All right. Should I follow the examples? All right, so now we have it. We have two equations. We don't know whether yielding going to occur first or fracture going to occur first. So we need to do both all the time. We do yielding and fractures both the times. We don't just blindly follow that this yielding going to occur or fracture going. We do both at all the times. Someone might say when you have a hole, there is more likely that fracture will going to occur. Fracture will occur. Fracture will go on. That is maybe true, but the standards does not say specifically that when you have hole, you just need to do the fracture check. We need to do the both checks. Okay, so for the completeness of the exams, let's do the both checks. So there are two options. One is yielding. Second option is fracture. When you have a yielding, these equations we can use. AGFY. AGFY. When you have a fractures, you can use 0.85, KT, AN, and FU. All right, so there is only two equations. I can show it to you both equation here on the clause 7.2 on page number 99. Clause 7.2 on page number 99. Right. How do you gonna calculate NT? NT would be minimum of yielding or fracture. Okay, so where is written? I can show it to you. Where is returns? I can show it to you. The nominal section capacity of tensor member shall be taken lesser of these two. That is minimum of these two. So that is lesser of these two, right? Let's find each values one by one. Gross area written here. AG, gross area of the cross sections. Now gross area, what sections we are working on? 75, 56 AU. Let me get the robots. Sorry. Here you go. Because if I open this one, that will be blurred on the screen. Let's go back to the. So I think unequal angles. Unequal angles is on the page number here on page number 24. All right, so what was that? 75, 50, and 6, I think. Yep, 75, 56. And the gross area is here. And for that gross area, we are taking 721. Everyone agree? 721 millimeter square. And so gross area, 721 millimeter square taken from one steel table, because we have 75, 50, 6 unequal angles. And we have two unequal angles. So we just have a AG 721 times by 2. 721 times by 2, we get 1442 millimeter square. Any questions in finding AG? We have two unequal angles, therefore we multiply by 2. So we are finding the combined capacity. Any questions in finding AG? It's just given in the one steel tables. Straight away you can use it. All good? So that is the equation AG. Now Fy, which is the yield strength, we can go back here. Here you go, 75, 75, 56, and yield strength is 320 on table 27 on this one steel tables, and that is 320. So 320 megapascals, or you can say Newton per millimeter square. Right. So option number 1, yielding. We can get it done. Yielding NT equal to AG Fy. AG was 1442 millimeter square times by 320 Newton per millimeter square. So 1442 times 320, you get 440 newtons. So you get 461.44 kilonewtons. So that is the first things we calculated, and that is the yield capacity. If you put more than 461 kilonewtons load, these members will going to start yielding more. That is the yield point. That is the boundary. That 461. That is the boundary. That this is the capacity of your 75, 50. If you don't put any hole, it can resist 461.44 kilonewtons. That's the yielding. If you put more, then it will reach into the plastic zones. Okay. Any questions? So physically, everyone understand? Keep an eye on the numbers all the times. If you're getting the 1 million kilonewtons, something is dodgy happening in the calculations. So just keep an eye on the numbers. These are light members. They are not heavy members. You can see they are just what's the thickness? 6 millimeter thickness. Okay, so they are light members. They use in the roof. If you check the roofs, they have this angle. If you look at those transmission tower, the electric transmission towers, they have these unequal equal angle that shows that they are light compared to those universal beams. Any question in finding the yield strength NT? All good. Move on. Question option number 2, that it can fracture, right? We don't know. The standards want you to check. So the fracture has equation 0.85 KT AN and FU. All right. You know 0.85 where is coming from, because this is, oh sorry, this is, let's say, fracture, this is FU, this is FY, and this is no hole. When you have some hole, let's say some hole, you will get this on FU. Let's say you have too many holes, you will get this FU. We don't know which FU gonna take. By the way, FU is 440 megapascals. It's frozen. Yep. It's coming up here. It's frozen up there. Yeah, therefore. Let's fix it. All right, we are back. Now let's see if you can see. So let's try again, because we missed that details. So this 0.85 that we talk about. Yep. So this 0.85. So we will say that, okay, if you do the laboratory test with no holes, this will fracture here. This is your 440 megapascals FU. And this is your yield FY 320 or 300 megapascals when there is no hole. Well, there is no holes. When you put some holes, 1 or 2, let's say you will get this. Let's say you get about 400 megapascals FU. Your FU reduce. We put a hole and it will fracture in the laboratory, let's say. Then let's say you put more holes, even you don't get 320. Let's say your FU become 300 megapascals. Now questions come from the engineer, which one to take? Right? Because it's 440, 400, 300, 200, and so on. So standard said, don't worry about anything. We done the laboratory work. You just multiply 0.85 with your FU, 15%. You can guess that is the capacity that you're gonna go down. So that is the 0.85 FU. Let's work out the KT first. KT, it is called correction factor. You don't need to remember the name again. The correction factor name is given here. KT, correction factor for distribution of the forces, determining in accordance with the clause 7.3. You are more than welcome to read. I think we read these lines on the lectures. The things that I explain you that. Now in here, in these tables, let's look at this one. Probably in the lectures we use this one. You remember that in the lectures we use this KT equal to 1 because we have these configurations. In the lectures we have, we have these configurations. The gusset plate was like this, and we have these configurations. You remember that in the lectures, right? Here you go. Right, we have this, and we connected these guys here. So for that case, we use this one. We use KT equal to 1. Now, in this workshop example, they say that you have this configuration now. This is your gusset plate, and your configurations is the short legs are connected here. Long legs are like this. Short legs are here. It's given in the examples that you have short legs, and it is bolting by M20 bolt here. Right? That is given here in the examples. Where is it? 2 short legs instead are connected to the single gusset plates, right? So 2 short legs are connected. So now in the lectures, as I mentioned, we use this one because we have gusset plates and we have back-to-back connections on that gusset plates. That is, we take it one. Now in the workshop examples, we have the short legs because we have one-sided connections because this is the one gusset plates and you all the connection are on the one side of the gusset plates, right? You have gusset plates, you have two sides of the connection. In these gusset plates, you don't have anything here. In these gusset plates, you have everything. So you have another plate here as well, by the way, that is not shown in here, but we have an unequal angle. That's correct. Connected by the short leg. Yep, short legs. You can take it 0.75, and that is the one-sided connections. Standards don't like it. Don't like it meaning that you have a non-uniform stresses generated due to these one-sided connections. Therefore, you have eccentricity. So therefore, we take KT equal to 0.75. So everyone okay with that one? KT equal to 0.75. Understand that? And here in this configuration, we take KT equal to 1. This is the back-to-back connection. It can classify because you have this gusset plate and you have a connection on the left and connection on the right. In these gusset plates, you have just connection on the one side. Therefore, we have KT less than 1, and that's KT equal to 0.75. Right? So that KT equal to 0.75 done. Net area equal to gross area, take away area of your hole. Right? So what happens here? We have these unequal angles, short legs. We need to create the hole, right? Because the boltings need to go through it, and it is M20 bolts. So meaning the diameter of the bolt is 20 millimeters. Now, if the bolt is 20 millimeters, we can't have 20 millimeters hole. We need to provide some clearance. So we can provide 1 millimeter clearance on each side. So the hole that we need is 22 millimeters. Right. So in that case, gross area we already calculated. Where was that? For two plates, gross area was 1442 millimeters. 1442 millimeters square. Now the area of the holes, this thickness is 6 millimeters. Where that coming from? Thickness of your plate is 6 millimeters. So thickness of the plate is 6 millimeters. So 6 and the hole is 22. So 22 millimeters times by 6 millimeters, you get 22 times 6, you get 132 millimeters square, and you have two holes because there is another side as well here. So 132 millimeters square plus 132 millimeters square, you get 264 millimeters square. So 264 millimeters square, you get 1172 millimeters square net area. One four four two. Take away 2 times 22 times 6. 1178. Oops, sorry, 1178. And 2 times 22 times 6, 264. Yep, 264. That's all good. Any questions? Finding the net area. It's just you need to take out the holes, the area of the holes, and take away from the gross area. It will just the net area that you require for the calculations. Anything else? I think the last one is the FU. That is the tensile strength. And in the graph, I show you the FU. FU is like that. This is the yield point. This is your FU. These points where you start going down is your FU. So that would be 440 megapascals. And this is your yield point, 320 megapascals. As a fractures happens generally after yieldings. If you don't have hole, so if you take a like a tensile specimen, you know tensile specimen, right? If you pull this tensile specimen, any materials, Then this part's going to yield first, so it will reach 320, and then it will separate it. Right? Then it will get like these separations. You got it? So in the normal situation without hole, but if I put the hole here, then you might not get these fractures, but still it will follow this kind of a trend, and it will fracture here, right, before yielding. So where are we gonna get it? If you go on this one, and if you come back here, 300 plus section tensile strength Fu is 440 megapascals. From the one steel tables that you can get that 440 megapascal for 300. So that is 440. Now let's find it. So NT equal to 0.85 KT AN FU. 0.85 KT was 0.75. AN 0.75, right? KT, yep, KT 0.75. Net area was 1178 millimeter square. Fu 440 Newton per millimeter square. If you just plug that one, 0.85, 0.75, 1178 times 440, you got 330, 429 newtons. Just take it 2 decimal places, 43 kilonewtons. So NT, final NT would be minimum of yielding or fracture. Where is written? Here. That you need to take a lesser of this and take a lesser of this. This is yielding, this is fracture. So minimum of yielding was 416.44, 461.44 kilonewtons, and fracture was 330.43 kilonewtons. We get 330.43 kilonewtons. Now final capacity, we need to multiply by the capacity reduction factors. Yesterday I told you, when you bring the members on the side, they don't straight. They are not straight, like they might have some, let's say you assume this one. Let's say you assume this one is straight, right? But if you just move it from one place to another place via truck transport, let's say Sydney to Melbourne, it might get some kind of this kind of behavior, like global behavior, global imperfections. If you do the weldings, it will create the residual stresses. It is locked inside the materials. So for that kind of accountants, we just generally want to have these 20% reductions, and that's taken into account by 70 these guys capacity reduction factors. And where we can get it? From the tables that we have. I think I show you these tables many times, but for this example, I can show it to you again. So these tables, you read these members subject to axial tensions, and you get 0.9. Almost everything is 0.9. Probably this bolt connection only 20%. So 10% reduction that they just applied for those residual stresses and all. All right. So section 7. All right. So finally, we get the final answer of 0.9 times 330, about 330.43 times 0.9, you get 297.39 kilonewtons. So final answers, capacity equal to 297.39 kilonewtons. Right? So that's the capacity of the members, two members. Capacity of that members means we can't load these members more than 297. If you put the loading 300 megapascals, 300 kilonewtons, not allowed. That is the capacity of that members, tensile members. So we don't allow to load these members more than 297. That's the answer. Now there are two kinds of examples that you come across, that you will have an analysis and you will have a design. Analysis meaning someone will give you, let's say 75, 56 unequal angle. They give you this, right? These examples, and you find this capacity of that members. in the design, someone say that my load, your design load equal to, let's say, n star equal to, let's say, 200 kilonewtons. And tell me the section size. Tell me the section size meaning. Tell me this is 75 or this would be 50 times 40 times. I'm just making it up. Equal angle or something. Tell us that. If you have 200 kilonewtons, that is a design questions where they give you the design load and you know how to calculate this design load. You remember that, right? In SD1, we have, let's say, truss members like this, and then you have this roller and pin, and someone say that 10 kilonewton comes here, 50 kilonewtons comes here, some dimension here, and some dimension here, something like that. And then you can calculate those tensile force and start internal forces. You know how to calculate that, right? So if you know this one, then you can design these members. That how much, what's the size of the members that you can provide for that particular. And particularly if you have 200 kilonewtons, your capacity that you're going to calculate should be greater than n star, right? And that is given here in this one, that your capacity of the member should be greater than your demand. That is the internal forces, right? Any questions there? So don't hesitate. If there is analysis questions, you can calculate the capacity by using two equations. If you have a design equations, you can assume it is yielding and get the gross area, and then you trial that one, and then you do the calculations. Right. Moving on to the next ones. Any questions or anything that is puzzling you or not making sense before moving on to the next one? As I mentioned, this is the easiest topic that in these subjects that we have, axial tensions. Not much happening because when the buckling comes, it gets complicated. You will see in the compression members next week. But in tensions, they generally don't buckle. It's just fracture. So it is easy for us to deal. So let's move on this one. A 300 parallel flange challenge. You might say, where I getting all these names? These names coming from here. Let me find parallel flange channel. Somewhere on equal angles. Equal angles, universal, yep, parallel plane channel, FC. That's given here. Which one is this? Is 300. So we are looking at this one, 300 PFC. Right. So there is 300 PFC is to be bolted on 16 thick gusset plates. So this is 16 millimeter thick gusset plate. I hope you understand this configuration, right? This is the 300 PFC. PFC meaning that you have channel. Oops. Right. So that is the flange. This is flange and this is flange and parallel. There are two parallel flange. So that is called PFC, parallel flange, and channel C. So that is channel. And what happens here? Someone come and do this bolting. So it's they connected these gusset plates here with the bolt with the 3 bolts. So this is this line is this line. This top line is this line, and they connected with the 3 bolts this configurations. Now, and the single rope. So there is a single rope, 3 bolts, and each bolt has a 20 millimeter size, space 70 millimeters. So 70 millimeters each space. Determining the design axial tension capacity of channel in this configuration. So we need to calculate the design capacity of we need to calculate 5 NT for 300 PFC. Again, this is analysis questions, not a design question, because the section is known to us. I think analysis questions are more simpler than design questions, but I think design questions are more challenging. It will challenge your understanding. But anyway, that's the analysis question. So again, you have two options. You have AGFY, which is your yielding, and you have a 0.85 KT ANFU, and that is fractures. You know the story now, right? That's coming from here. That's yielding and fractures, right? Close 7.2 section 2. I think this is repetitions. I think I don't need to show you, but let's say for the completeness of this workshop, I can show it to you. But I think this is just a repetition, just a different sections. The configuration is different because there is a gusset plates and now bolted. But anyway, let's continue. So let's say we do the yielding first. Yielding gross area times Fy. Let's find the gross area. The gross area you will get. Here you go, gross area, and this will be 5110 millimeter square. So 5110 millimeter square. Let me keep my solution handy. Yeah, that's all good. 5 millimeter square. Fy. Okay. Fy is 300 PFC, and we have three kind of Fy and the wave. I think if I was there, I would consider 300 instead of 320 because that is the smallest value. So let's say you have 300 megapascals for that and 300 megapascals. You have two options. Take it minimum. That will be conservative. Conservative means it's going to work for both. Yes, please. You could. That is not an issue, but the whole cross sections we are designing it. We are not designing it like break it down the wave like we done in the bending, that we just take the wave out and we take the flange out. I would consider this is because with these anti equations that we see, that is for the whole cross sections. So there are weak 300 and another one is 320. So otherwise I cannot take 310 because it's in between. But to be conservative side, I would consider 300 because when you consider 300, it will work for 320. It will work for 310. So I would consider minimum 300 megapascals. All right. And I think, as I mentioned, there is no rules. The standards does not say how you're going to reach it. But if you take it 320, would not be any issue. But I consider take it 300. That will not work. It's conservative. It will work. So NT equal to gross area is 5110 millimeter square, and the yield strength 300 Newton per millimeter square. Use the calculators. 5110 times 300, you get 1533.00 newtons. So that is 1533 kilonewtons, and that is the yielding. If you don't have any hole, these channels will going to resist 1533 kilonewtons, right? And if you put the holes, they will have a different story. But that is the, and we do always both checks. So that is the yielding, first one done. Now second option is to have a fracture. And fracture has a simple equation. Now I remember without even looking, KT, I think AN and FU. I think I done it. Maybe this is 10 times. So that's the equations, and this is close 7.2. Right. You know 0.85 now, right? I don't need to explain you this one again. 0.85. It is straight over there, but that 0.85 comes from, you know, this different FU because of the holes. Now KT is correction factor. All right. in the KT correction factors, as I mentioned, these tables are divided into two zones. The top zone is the first port, which is the one side connections, and another one is the back-to-back connections down here. Right? Now, I can see there are not two plates. That's we have gusset plates, and these two plates are not connections, so we don't have back-to-back connections. So I have 4 cases that is on the top because it's a one-sided. You have gusset plates, and you have only one 300 PFC attached to that gusset plates. So in here, you can see this is a gusset plate, this is a gusset plate, this is gusset plate, gusset plate. Probably this is the closest one. You have parallel flange, and this parallel flange is connected with this one. You might ask, that is not, I cannot see exactly the same thing, but I think that is the closest fit that we can see. Again, this tables is expected. It's not give you all the cases that you're going to come across. Right? So closest parallel flange, and as I mentioned, you need to imagine. And if someone say that how I'm going to imagine, so if let's say if I hold these guys, with the 3 bolts and these guys are free, if I pull this end, like this end is pulling red one, what gonna happen? This guy will have a less they have a resistance, but this guy will come out more. So it's a non-uniform. So therefore, KT equal to less than 1 and it's 0.85. So you always feel, you don't just randomly take. So KT equal to 0.85. We give 15% reduction due to non-uniform stresses. So that is KT. AN equal to gross area minus area of the hole. Gross area we already calculated, 5110 millimeter square. Area of the hole, how many holes we got? 3 holes, right? So we have a 3 holes. Now M20 bolts. So M20 require 20 millimeters of holes. As I mentioned, we need to provide the clearance. So you have 20 millimeters of hole, and the thickness of your parallel flange. We don't need to take the thickness of these gusset plates. You need to take the thickness of this parallel flange. So the thickness of this parallel flange would be, we will take the thickness of the wave. I think the 8 millimeters, or how much did you take? 8 millimeters. So I hope you understand that. So this is 8 millimeters, by the way. So 8 millimeters. So 8 millimeters would give me 3 times 22 times 8. You get 528 millimeters square. So 528 millimeters square. Net area is 5110, 528. You get 4582 millimeters square. Net area done. I think we are almost there. 0.85, 80, 0.85. Net area 4582 millimeters square. Fracture FU 300 plus 440. So you get 0.85 times 0.85 times 4582 times 440. You get 1456617.8 newtons, which gives me 1456.62 kilonewtons. Right? So NT would be minimum of yielding and fracture. I'm just writing it up, okay? Because I think this is repetitions. I think you are smart enough now to crack this one. 1456.62 kilonewtons. So you get 1456. It will control by fractures. It will fractures before yield. That's graph that I show it to you. This is yielding, and it will fractures before yield. Right? So it will not reach this point. This is yield. This is fracture. So fracture will control. 5.9, 10% just gone. because of, you know, this imperfection and all that we cover in the lectures, times 0.9, you get 1310.96 kilonewtons. That's the capacity of your plate. So you cannot pull more than 1310. So this pull that you have, you cannot pull more than 1310 kilonewtons. You cannot, otherwise this will fracture here. That will fracture at here and you will have a separations that we don't want it. All right. Any questions? Anything that's not getting through? Only these tables is a little bit tricky, but I hope you get a message to use the tables. Now the last one. Rework questions to be welded to the gusset plate instead of being bolted. What happens here? They say that this bolt is not there. Let's say let's put this gusset plate. This is a gusset plate and we have another member here. And instead of bolting it, we weld it. We don't put the holes. We weld it through this same examples, everything's same. The difference is someone said, I don't want to bolt. Let's do the welding. See that configurations, right? Exactly same. What going to happen now? Because then yielding and those I think I can go back and do it. I think yielding wall will not going to change. This one here, NT, we will going to take the same 1533 kilonewtons. NT yielding 1533 kilonewtons. That no change because just the same cross sections, everything same, and yielding is regardless whether it's going to be bolted or not. That's yielding will, because yielding assume there is no holes. So your AG would be same, your FY would be same if it is bolting or weldings, right? Not much difference. So in that case, 1533. Everyone agree with that? Now the difference here, it comes in the fracture, because fracture generally controlled by holes that we put it into the flange of that members. So we have equation 0.85 KT net area times FU. Now we don't have hole. Look at this. We don't have any holes in the PFC parallel flange. So your net area equal to gross area. Do you agree with me? That your net area equal to gross area because we don't put any holes in that. What was the gross area? Gross area we take 5110. 5110 millimeter square. Everything is same. 0.85. KT is also 0.85. Gross area is 5110. And your fracture is 440 Newton per millimeter square. Right. So this is the only difference. Right. When you do the welding, your holes are not there. Your net area is equal to gross area. So if I just plug into that one, 0.85 times 0.85 times 5110 times 440, you get 1624469 newtons. Look at that, 1624.47 kilonewtons. In the previous examples, the fracture was the dominant. Fracture was the governing factors. In here, yielding will be the governing factors. Now you can see that NT would be minimum of yielding was 1533 kilonewtons and your fracture was 427 kilonewtons, right? So your yielding would be dominant as you can see, there is no holes. For that case, 1533 capacity factors 0.9, 1533, 0.9, 1533, 1379.7 kilonewtons. Right. Someone might say, welding is good. Yeah, on the paper, welding is good, but it's difficult to someone go up there and do the weldings. And we need the licensed good welders. It's not that you can send someone and they do the weldings. And generally, weldings would be very critical and weak points in this one because weldings are brittle. They heat it up the materials, and as you know, when you heat up the materials, they reduce their yield strength. The surrounding, we don't consider this one in our subjects, but when you heat up the material and when you see this one red, it becomes brittle. When it's cooled down, it becomes brittle. It's reduced 300 megapascals you are considering, you are not going to take 300 megapascals. You might reducing 200 megapascals. It's not part of these subjects, but that is sometimes you need to take into account that one. Any questions or any